Welcome to our inaugural episode of the Moor XR Insights podcast. It's the latest in everything from augmented reality to virtual reality and everything in between. And it's brought to you by Moor Insights and Strategy. I'm Anshel, Moor Insights and Strategy Senior Analyst covering XR, 5G, smartphones, and PCs. And let's get started. This week, we will have three guests on the podcast in a panel format to talk about the latest developments in VR centered around foveated rendering with Tobii's Johan Hellqvist, NVIDIA's David Weinstein, and HP's Henry Wang. So let's get started with the first questions. First, I'll have you guys introduce yourselves. So please introduce yourselves.
Yeah, so I'm Johan Hellqvist. I'm working at Tobii. We do eye tracking, and I'm heading up the XR segment within Tobii, focusing on integrating eye tracking into devices.
I'm Dave Weinstein. I'm Director of Virtual and Augmented Reality here at NVIDIA.
Henry Wang. I work at the VR group in HP, and I'm Product Manager of the HP Reverb G2 Omnicept Edition headset, which is launching next month.
Thanks a lot, guys. So I guess we can start out with kind of a level set, and I'd ask, where is eye tracking today versus a few years ago, or even where was it before it was implemented in VR? And I'll start with Johan, but I'd love to hear from all of you.
Yeah, so I think if we look on eye tracking in VR a few years back, and even stepping a little bit further back, historically, eye tracking has been around for more than 20 years in modern format, starting out in scientific usages and assistive usages. When we started in VR, we also came from the scientific field where you had a selected group of people who could kind of do eye tracking. 2018, we kind of launched our first commercial headset for OEMs. And the main focus we put in there was for it to work on many people and have a good enough accuracy and precision from the eye tracking point. What has happened the last year is that we have continued that route. We see that the more we're moving from establishing ourselves in enterprise and moving into consumer, the more you need to guarantee that it works for everyone, which is, it's relatively easy to make a simple eye tracker. It's darn hard to make one that works for everyone. And we also released a couple of headsets. The most recent one is with HP, the Omnicept edition, which we're really thrilled about. And beyond the eye tracking part, we also kind of work with partners, NVIDIA here, for example, to lower the barriers using eye tracking and showing the real benefits of eye tracking moving along. And I think we've made huge steps just the last 3 years, and we assuming that we will continue that trajectory.
Yeah, and I think to add on to what Johan's saying, I think where the market is in terms of expectations and customers are really aligning with how the technology is progressing. You know, when we first talked about VR, a couple of years ago, it was always about the promise that that eye tracking could bring to VR experiences. But late last year, when we launched the standard Reverb G2 headset, we would be talking to customers, and the whole pitch around the Reverb G2 would be barely out of our mouths, and before the customer would just interrupt us and say, "Okay, that's great, that's super exciting. When's the eye tracking version coming?" There is almost this expectation that eye tracking is here and has truly arrived, and that I think that is exactly what we're seeing now with the launch of our Omnicept edition of the headset.
I think one of the, just to chime in on that, one of the exciting things about eye tracking inside of a VR headset is it really starts to differentiate VR rendering from traditional monitor rendering. If we go back a few years, VR headsets were basically, take a monitor display, shrink it down, take a couple of them, and cool, we have VR. But there's so much opportunity to differentiate it. Like, that made sense as a starting point because that was the graphics pipeline that we had. But when you really think about graphics and what you want to show to a person who has a VR headset on, you could render a ton of pixels, But in reality, they're only seeing a very, very small percentage of those pixels, right? And so this concept of eye tracking kind of turns the graphics pipeline on its head. It says, don't render the entire screen, equally. There's no reason to do that. That's a waste. Instead, there's all these optimizations. There's all these things that what we can do when we make computing more personalized. And the VR headset is just a perfect example of that. So, over the course of this discussion, hopefully we'll have time to talk about it a little bit. But ray tracing is the right technology if you know where a person is looking, right? And so again, it's kind of reimagining the whole graphics pipeline, and gaze tracking is really the first step in that.
Great. I guess that tees me up for the next question, which is, what are the key technologies that have enabled the advances that we're seeing today versus what was possible in the past?
So if I'm on the eye tracking side, we see that as David were alluding to, that using eye tracking to kind of optimize where you focus your graphic resources on is where we have spent a lot of time investigating. I know that NVIDIA has been doing that for quite some time. When it's come to the eye tracking part, I was saying before that it's need to cover a full population. That's one thing. The other thing is that we've seen that the characteristics of eye tracking signals when you do foveation is slightly different when you are using interaction, for example. With in foveation, it's extremely important that you actually are hitting the area where you want to optimize your graphics, and you want to do that all the time consistently. So we actually have a different signal and different concept around eye tracking, even feeding, like in the Vrss case, the signal directly to the driver, to the NVIDIA driver. And we've separated those signals for those reasons, because they're optimized in different ways. And we call that Tobii Spotlight when we've optimized that portion. And I think those two in combination are the main events that has kind of enabled foveation to be really as good as it is right now with the VRSS2 and the coming headsets. So that's the key drivers, I think, from an eye tracking perspective.
David?
Yeah, I mean, there's a ton of technologies that come to play here. In terms of the actual eye tracking, I think Johan covered it really well. The next step then is, cool, I've tracked the eyes, now what do I do with it, right? And that's when these technologies like variable rate shading really come into play, because as I was mentioning before, if you know where the user is looking, suddenly it's a different ballgame. Suddenly your rendering problem isn't render as many polygons as you can, as fast as you can, and make them all look gorgeous. Suddenly it's make the portion of the screen that the user is looking at or that they care about look gorgeous, and the rest of it just has to be good enough, right? So VRS is technology that we'll talk more about later in the segment, but just to kind of lay the foundation for it, the whole concept. So VRS stands for variable rate shading, right? And it's an industry standard. NVIDIA first added support for it, first implemented it with our Turing architecture, so previous generation. But the whole idea is, let's take the screen and break it up into 16 by 16 pixel blocks, right? So if you have a 4K you can imagine, you have a pretty fine tessellation of these blocks. And for each of those blocks, I'm going to specify the shading rate that I want to use within that block. And so this gives you really fine-grained control over where you're going to spend your rendering resources. And on top of that, there's all sorts of great technologies that you can build, such as VRSS, that we'll get into.
Perfect. I guess the other question, and this one's a little bit more focused directly at Henry, which is, what are some of the challenges of building next-gen high-resolution VR headsets like the Omnicept that are kind of pertinent to this discussion around foveated rendering?
Yeah, I think everything that Johan and David talked about is certainly exciting, and what really helps it stand out is coalescing that with a headset, or providing that headset that really puts those in the spotlight, so to speak. It really puts those at the forefront and makes those benefits shine. And if you've looked at our progression within HP in terms of our headset portfolio, moving from Reverb Gen 1 to Reverb Gen 2, one of the things that'll stand out immediately is from Gen 1 to Gen 2, on a pure pixel count, that didn't change. It's still 2160 by 2160 per eye. It's still that, very high industry leading resolution amongst major headsets. But it's because at that pixel density, we've really solved a good amount of that, what people perceive as a screen door effect. But then with Reverb Gen 2, if you actually put it on and do a side-by-side comparison of Gen 2 versus Gen 1, you'll notice immediately that despite it having the same resolution, the visual experience is much improved. And that's because with Gen 2, we work closely with our partners at Valve and Microsoft to really look at what are the other aspects of the visual experience that we can bring to bear and improve, particularly, with our relationship with Valve, them bringing expertise in optics and improved lenses really helps with the clarity, so that yes, you're getting a high pixel density, but you're also viewing those through lenses that do it justice. And then what that enables then to move from Reverb G2 to Reverb G2 Omnicept Edition is for the focus to then turn to the rendering pipeline, to what David talked about with VRS and VRSS, what Johan's talking about with Tobii Spotlight, and to improve the rendering pipeline as well, so that from kind of the top of the stack with the application all the way down to the headset level and the components, the displays, the optics in the headset, we're really seeing a full kind of holistic improvement across that entire stack. So that's really what we're seeing here with all of these different elements coming together in the Reverb G2 Omnicept Edition.
Yeah, and you mentioned VRSS 2.0. I was kind of curious, like maybe David can answer this. How does VRSS 2.0 work, and what are the underlying technologies, and how is it different from VRS?
I'm so glad you asked that, Anshel. So I'm going to put on my professor hat for a second and sort of walk you through what VRSS is, and kind of how 2 is different than 1. And I think that'll answer your question. So I mentioned earlier on that, VRS, variable rate shading, is kind of this core underlying technology. And then there's all sorts of things that you can build on top of that. So what NVIDIA had noticed after we published our VRS SDK and we were encouraging developers to use it is there are a lot of developers, everybody who's building a VR application is on a tight budget in terms of time to bring out their new game, their new app. And so they don't always have time to invest in new technologies. Ultimately, they do when they see how great they are. But anything that's going to slow down the process is going to be a challenge. And so what we did with VRSS is we said, we know that you will see improvement in your game quality and your visual quality by using variable rate supersampling. And so what we're going to do is we're going to make that available to developers as a zero coding solution. In other words, you already have an application, you've already built your app, it's already been released. We can still make it run better with higher image quality. And the way that we did that was inside of the driver. So developer didn't have to do anything. Inside of the driver, if you have headroom, okay, so a VR frame has a budget of roughly 11 milliseconds, right? 90 frames per second. So let's say that you completed rendering that frame in 9 milliseconds. You have 2 milliseconds left. And there's no advantage to sending that frame to the headset early. It's not going to do anything with it. So let's take those 2 milliseconds and improve the visual quality in a specific region within that image. And with VRSS, we said, we'll do it right in the middle of the image. And so we basically take a circle, and users tend to look forward in VR, and we improve the image quality, again, using that VRS technology. So in the driver, we create a VRS grid, and we say in the region in the middle, we're going to do a higher sampling rate, right? And so we released that with a little over a year ago, year and a half ago, and that was called VRSS. It was VRSS version 1. And people loved it. It got adopted by a bunch of games. Of course, they love it. Developers don't have to do anything. Users just see the benefit of it. The problem with it is people aren't only looking straight forward inside of VR, right? Yes, you turn your head a lot, but you also, move your eyes around. And so a better optimization is let's improve the visual quality where the user is actually looking, but that requires gaze tracking, right? And that's where this whole partnership came from, working with Tobii, because there needs to be this tight coupling between the gaze tracking hardware and libraries, and then the driver, which is going to have to receive that information, and then of course a headset that would take advantage of it, right? So you're seeing the pieces come together here. So with VRSS 2, that was the further optimization that we made. So in real time, we're receiving this gaze tracking information, and we're using that in order to build the VRS map, which increases the image quality in that portion of the region of the image where the user's looking.
So maybe I can take one step back on what is kind of foveation. I mean, if you have your visual system, your eyes, it's actually a relatively crappy system from a sensor perspective. You only have focus on your thumb, where you have high resolution focus. The further you move out, the lower the resolution, and when you are in the periphery, it's actually black and white. So the impression that you get that you have perfect vision all over is just a brain construct. It's your brain kind of interpolating where you're looking, and the same method is used for graphics, or it could be kind of where the user have focus. You can do optimization. In this case, we do graphics optimization. I think when you measure an eye tracker, you can't be pixel accurate. It's a sensor system that absorbs you. The better it is, the smaller the area can be, the larger the saving. The shorter the latency, the more you can shrink that area as well. So we've been working very much to get that consistent and deterministic with a very short latency. That's also, as David were alluding to, we are connecting directly into the driver to kind of cut every kind of latency, and the signal will get used as late as possible in the rendering pipeline to add a little latency from when I'm actually looking to where it actually gets rendered. And that is kind of a concept that is fundamental to any foveation. So now we're looking at VRSS, and there's future things that we can do as well. And when you have a headset like the Omnicept edition, you also are very sensitive that if you only do it in the middle, if it's static, you're wasting all your nice optics that you acquired for a lot of money. And you want to have absolutely the best performance per pixel, and you want to look around like you do in reality. And that's why I think this is a great marriage now, a three-party marriage, and it's actually now starting to work better and better. VRS worked, and this is working even better. So I think it's a great progress moving forward. And you mentioned ray tracing. That will also be interesting.
Yeah, you make a really good point, and I'm glad you brought that up, Johan. As you, I think it's useful. People have a good picture in their head now, thanks to your explanation, that where you're looking, the size of your thumb is sort of the foveated region. I've mentioned that VRS is going to increase the image quality maybe just double clicking on that for a second, what you notice within that VRS region, if you were to pause the screen and look at, what's the fidelity outside of that region, you'll notice that within that, that super sampled, that VRS region, you can read text much more clearly. You're essentially super sampling, right? You're super sampling within that circle. And so everything becomes clearer there. Your materials have much better accuracy. You have much, you get away from sort of flickering artifacts and aliasing. You're able to read text. And, as you were saying, you're nearly blind in your periphery. So, it would be a waste to be doing all of that super sampling work, out in those regions.
I think there's a couple of nice pictures and small movies that we can publish as well.
Yeah, we'll have some of those queued up. You can watch during the video podcast if you want to tune into that. But the audio podcast, unfortunately, doesn't have visuals.
It looks great.
Henry, did you have any insight, or did you want to move to the next question?
Well, I think something that I would like to reiterate, that David mentioned kind of at the start of this topic was the fact that VRSS is now available without any additional coding necessarily on the developer part. That really can't be, the importance of that can't be overstated, right? Because if you think of VR developers these days, they are often they are looking at their resources and their bandwidth. What can they do? They have new applications to create or existing ones to update. And as they're sorting all these out, to be able to deliver all these great benefits that Johan and David talked about without any, really additional work on their part is huge for the adoption of the technology. And really that'll, filter down to the end user, and as more end users see the benefit, it kind of creates this feedback loop, right? Where as more end users see it, they start to expect that more and more, and they are asking for that from developers. And for a developer to look at that and say, well, this takes no additional work, well, that's a no-brainer. Of course, I'm going to make sure that it works with VRSS. That's only going to improve VR experiences everywhere.
Yeah, so it might be worth taking, I'm glad you brought that up, Henry. It might be worth taking 30 seconds just to mention that there is, it's no coding, zero coding, as you said. But there is a process. We want to make sure that VRSS does work great with those apps. And so developers just need to pick up the phone and call us, basically. So send us the app, we'll double check it, make sure that it is seeing the image quality benefits that we expect it will. And then we just add that to the allow list in the driver. And then users can just turn on kind of a, per application, they can just go turn on the application in the NVIDIA control panel to then take advantage of those settings. The application does need to be DX11 and forward rendered, which most VR applications are. And then, of course, it has to have a MSAA buffer, because that's what we're going to use for the super sampling. But yeah, super easy.
Cool. Thanks for the explainer. I appreciate it. HP's new Omnicept is the first headset to integrate a lot of new sensors and capabilities. And how does foveated rendering make it different from the standard Reverb G2 from last year, or well, from this year, I guess? And what are some of the applications that you guys can think of that make sense for this new headset?
Yeah, so I think Johan and David talked a lot about how foveated rendering works, how it really optimizes around how a human visual system works, and I think when you look at the effect that has on the visual experience, going back to what I talked about earlier in terms of where we went from Reverb G1 to G2, and then now G2 to the G2 Omnicept edition, and taking that a step further and making sure all of the improvements in Gen 2 visually are accentuated even further. I think what we're seeing is for a commercial oriented device like the Reverb G2 Omnicept Edition, we're looking at a lot of use cases like product design and AEC, where the absolute accuracy and detail really matters, as well as training that has fine text and detail. A lot of these use cases where you're training, say, on if you're a maintenance technician training on a new piece of equipment, a lot of times text, labels and such are a big part of that training experience, or a big part of the usage of equipment. And so to be able to really make those finer details come out even more, super valuable. And it really plays well, of course, with the insights that eye tracking, as well as the other sensors on the Omnicept Edition headset, like heart rate and face camera, bring to the table. So those are kind of the use cases where we're really seeing this have an impact, and really super excited to see what developers do with all of that.
And I think one more thing, I mean, we're talking VRSS2, which is the focus here, which kind of enhances textures and text. I think if you have an application and you want to really utilize the graphics in the Omnicept edition, you could but you still don't have enough frame rate, or you don't have enough graphic performance. Then if you have a little bit more development time, you can actually use VRS, which is kind of downsampling and focusing your full graphical power on where you want. So that's the beauty of this concept of that NVIDIA has, that it's either you have no coding and you just enhance, or you do a little bit of coding and then you can get even more horsepower out of what you need to kind of make your application absolutely brilliant. And it's the same concept, but you need to add a little bit of work on your application. Whereas VRSS is kind of no coding, just go contact David, not maybe him directly, but NVIDIA, and get it done, and then you run it on your HP device.
That's a good point. One of the things that we've seen people do when they take advantage of the full power of VRS is that, in addition to foveation, which obviously you can still do foveated rendering with full-blown VRS. People are also using it to do what's called content adaptive shading. So if I have objects in the periphery that have a high frequency texture on them, like maybe the carbon fiber of the hood of a car, what you'll see with sort of normal rendering is you can get some flickering and popping out in the periphery where that car hood is. And so with full-blown VRS, you can say, okay, for that texture, for that material, wherever it shows up in my scene, I want to super sample. And where the user is looking, I want to super sample. Oh, and I want to take advantage of the fact that I kind of know how the optics work in my head-mounted display. And so you can really kind of fine tune it in, if you have the budget to take advantage of all that VRS offers.
Cool. And I guess that kind of leads us into more questions about the Omnicept specifically, kind of around this Omnicept sensors and the SDK. And how do you guys see the new Omnicept SDK changing the way VR moves forward? I kind of want to start with Henry, just because he's the expert on the headset.
Yeah, so virtual reality is already being valued greatly in a whole host of use cases, a whole spectrum of industries, for its immersion, for that immersive experiences, and the impact that has in these use cases in training, collaboration, product design, etc. But the vision around Omnicept is to really push that a step further and make experiences user-centric. So how can you improve both the experience while you're in the HMD, as well as the outcomes, by adding inputs and adding insights? So, the Omnicept edition of the Reverb G2 has, of course, eye tracking, but it also supports pupillometry with those same sensors, as well as has a PPG sensor that can measure heart rate. and then as well as a face camera that looks at the mouth and lower facial area. But really what those mean for the end user is having insights from eye tracking, as well as the Omnicept SDK, having the capability to collate all these different sensor inputs into a machine learning driven cognitive load insight. So you understand how cognitively loaded is a user during experience at different points in the experience. Because if you think of a lot of these use cases where for VR, whether that's design review, whether that's training and simulation, you know, the VR experience isn't just limited to within the headset. Certainly, while you can change the experience within the headset to adapt to how a user is responding to that, it also extends to after the VR experience. So, say if it's a training example, having an after action review where you're looking at, okay, at what points in this procedure that you're training on did you react in a certain way, and how does that need to be tweaked? How does that need to be, you know, fixed for the next training rep? You know, to be able to have that active feedback loop that, and with all these extra inputs, really has a direct, tangible benefit of these user insights, enabling expressivity down the road with both the eye tracking as well as the face camera really enables collaborative experiences to become more engaging, more, you know, well, collaborative, as collaboration is really coming to the forefront, especially, you know, kind of in this COVID environment where we live in, where a lot of things are moving to virtual. So being able to really bring these tangible benefits of user insights, but then also setting a precedence in terms of security and privacy, with how the user insights are handled and how they're being utilized, how they're being stored or not, right? That's also a key pillar of Omnicept and the Omnicept SDK. So really it's all about adding more insights into it. And to go back to one of the things David was talking about earlier in terms of how VR is really transforming in terms of it's going from just displays in front of the user's eyes. It's all about making that kind of a more full-fledged suite of inputs, and then the VR experience adapts based on these inputs, more so than just pure headset tracking, more than just controller tracking. It's also these other physiological inputs as well.
Yeah, I think your training and simulation example is a very good example, because if you are a hazardous environment under stress, for example, you may be working with tools, and with the Omnicept edition with eye tracking, you can kind of, okay, my hands are occupied, but I can still kind of select things with my eyes to kind of interact with the application. You may have a guide or trainer telling you, no, don't look that much to the right. You should look more to the left, to the center of the fire. At the same time, you can measure the cognitive load of that person, how stressed out is that person. And in aftermath, you can see, okay, did I actually look at the right stuff? Did I pay attention to what I was supposed to? Did I pay attention to if something was happening at the right place? So I think you have all those three kind of pillars of interacting, how to do proper insight, how to measure the stress level, and provide fantastic graphics with some foveation.
Yeah, I really like the term that Henry used of user-centric, experiences, user-centric computing. The promise of VR is that it will bring us all closer together, right? We don't have to physically be in the same space, but we can, through VR, we can feel like we're in the same space. But what we saw with the first, the beginnings of VR was pretty isolating, right? You put on your VR headset and now, you are completely separated from the physical world. And so this promise of, having the pendulum swing fully back the other direction, I think is great. And I agree. I think that, anytime that you're in a training situation, anytime that, in real life, you would imagine having a mentor or a supervisor there, having all of these sensors is super, super important. because the mentor or the trainer who's there with you is kind of keeping an eye on you. They're seeing how you're doing. They're really kind of tracking your performance and trying to get those insights, and having all those sensors provides that data. There's a really good deep learning problem of how do I take all of that data and then turn that into a stream that an intelligent agent can then act upon. But we're good at deep learning. We're not afraid of that. And so, yeah, I think that the promise of VR bringing us together, allowing us to collaborate, really hinges on having more and more sensors in these headsets. The mouth cam to measure smiling and expression, and all the different eye cameras and engagement, and that's what's going to make it feel like we're together is all those sensors.
That's great. I really appreciate it. I think this has been a very interesting time for our industry, because I don't think we've really ever had as much focus on the user as we have today, thanks to all the new types of sensors and software that's enabling it from all different angles. So I think it's great. And that kind of leads me into expanding some of these capabilities outside of a PC experience, specifically PC VR, what ways that VRSS and foveation couldn't necessarily be used outside of a PC VR headset. I'd love to hear where that could be going today.
I'll take a first stab at it, and then I know Johan has some to add. So one of the trends that we're all seeing in computing is people are moving more and more of their compute, which can be VR experiences, could be anything, into the cloud, right? And that makes a ton of sense. Having compute on demand as much as you need when you need it is just a fantastic promise. It brings with it some huge challenges for VR, right? VR and AR are very latency sensitive. It cannot be the case that that I can wait 200 milliseconds for my image to come back, right? We all know that you roughly have 20 milliseconds for motion to photon latency from the time that I start moving my head to the time that the image has to update. And so while VR is now taking hold, it's at first blush a little bit incompatible with this idea of pushing more and more of our compute to the cloud. Until you recognize some of these opportunities that we have that Johan and others were referring to earlier, if we take advantage of the human visual system and the fact that, yes, I have to update the photons very quickly, but those photons don't have to be exactly right. It's just that the world needs to move, right? And similarly, if you kind of dissect the graphics pipeline, there are things that you can do in the cloud, like indirect global illumination, that no one notices if it takes 200 milliseconds for global illumination to update. So dissect that graphics pipeline, put things that have to happen very quickly with low latency, very close to the headset, and you have a winning strategy. And that's that's what we're doing with Cloud XR, which is NVIDIA's XR streaming SDK. So we do the rendering in the cloud. We do some small amount of rendering locally on the headset so that we can move the image as you quickly move your head. And it makes things like streaming possible. And it's absolutely compatible with technologies like VRSS.
I think to kind of add on to David and just show my thumb again, it shows where your user has his or her attention, and you can use that for enhanced graphic. You can do that to compress the image being sent from Cloud XR to the headset. It can be if you are in an AR environment eventually, or even now you want to do a lot of AI depending on where you are in the environment. You can't compute on everything, but you should compute on where you have your attention. And that's you can have foveated AI compute, probably want to trademark that, but as one thing. And when it comes to split rendering. I mean, cloud, to have everything in the cloud in 5G is one thing, but just having tethered headsets, wirelessly tethered headset, you need still to get the image from the PC to the device. There you can do foveated transport as well. And when it comes to latency, actually the hand controllers is probably the most difficult part to manage if you also include the action button pressure, whereas the eye tracking is relatively fast. So I think on top of that, the brain is relatively easy to fool. I mean, that's all the magicians, that's their work. So you get away with quite a lot as long as you don't have flickering and strange artifacts. So I think there's a lot of nice use cases where you can use foveation to kind of get better utilization of resources, basically. You only use resources where you're looking, whether it's bandwidth, graphics improvement, where I do AI or whatever. It's just it's a fundamental how we are built as a humans, and I think we should mimic that when possible.
I was gonna say, I think shifting the whole idea of utilizing foveation to help shift around where the compute lies is certainly something that there's an appetite for out there on the market. You know, I think we get HP, we get a lot of questions around, well, I love the power of having a PC VR driven experience, but I do want to be able to cut that 6-meter cable tether. So how can I have the best of both worlds? How can I have that mobility and ease of use, but also with that same fidelity that only high power compute can deliver? You know, we get a lot of these questions around, well, how do I make this happen for multiple users in the co-located in the same space, you know, across location-based entertainment, again, training in a lot of simulation use cases as well. So the potential of, you know, foveation in whatever form it may take in reducing requirements so that we can be shifting around where the compute lies, certainly gives customers a lot more flexibility in the deployments. And I think it's something that is definitely being asked for.
Yeah, I was just going to mention, Johan was talking about, you know, AI foveation, and if people have a few minutes on their hand, you can Google peripheral metamers, and there's some really cool examples of them. Basically, as long as the periphery has the right statistical properties, right, based on, you know, kind of the rods in your eye and what they view, you can make all sorts of crazy things in the periphery that don't resemble the actual periphery at all. And as long as it has the right statistical signature, your eyes, your brain is completely fooled, right? And so using AI to fill in those details so they have the right statistical characteristics, but can be much, much lower bandwidth in terms of, you know, foveated transport, and as well as, you know, in terms of rendering.
Yeah, and I was going to say, since we're on the topic of cloud applications of VR, what would you guys say are the top applications that would benefit from foveation that are in the cloud or would leverage cloud computing?
From my perspective, any application that where you render content in the cloud and that you need to send that content down to the display or the headset, there you can benefit from foveation.
Yeah, I think, you know, one of the trends that we're seeing is headsets continue to increase in fidelity, right, higher and higher resolution. And to Johan's point, you know, if you can compress the image intelligently, thereby not losing any fidelity where the user is looking, you can continue to feed all of those pixels. And the thing that enables that is gaze tracking, right? Because if you can do that, you know where you have to maintain the fidelity. So I don't think it's necessarily the case that, oh, this application will benefit, that one won't. It's kind of a necessary technology if you want to feed the high resolution and high frame rates that headsets are moving towards.
Yeah, and to expand upon that point about the broad applicability of foveated rendering, it's not just limited to a single type of VR deployment, right? When people think about cloud-based applications, a lot of times people's minds jump to, well, it is very much a server farm, and maybe it's pushing over, a lot of people are talking about the promise of 5G and those more mobile wireless technologies, but it's also these kinds of deployments can also manifest themselves in kind of on-prem edge deployments. So having a set of workstations on site over a wireless network with the headsets. That's another area where foveation can also play a huge role in reducing those bandwidth requirements and making those kinds of deployments possible. So I think really the possibilities are truly endless with this.
Johan, do you have anything to add?
I don't have, no, I think very much of it was said. Maybe the only bandwidth also means money. If in 5G, for example, you pay typically per bandwidth. So if you can reduce the bandwidth, there's money to be saved. So there are kind of some pure economic interests in that as well.
Great. Well, I think that kind of wraps up our discussion. I want to really say thanks to Henry, David, and Johan for participating in the discussion. We hope our viewers and listeners found this week's topics interesting. If anyone out there would like to provide us insights on a specific XR topic for a future podcast, please reach out to us on social media. I'm at Anshel, and we wanted to say thanks to Tobii for sponsoring this podcast episode. And we hope you have a great weekend, and please tune in again next week.